Imagine you are an explorer, not of distant lands, but of a distant star, our star, the sun. We see it every day, a familiar, warm light in the sky. It feels constant, unchanging, a reliable source of daylight. But what if I told you that this calm yellow ball is a place of unimaginable violence and power? What if we could peel back its layers like an onion and journey to its very center? Today, we are going to do just that. We will embark on a mission, a deep dive into the heart of a star to uncover the secrets hidden within. Forget what you think you know. The sun is far more strange and wonderful than you can imagine. Our ship is not made of metal or steel. It is a ship of the mind, built from curiosity, guided by science. We will need it because the environment we are about to enter is the most extreme in our solar system. The journey will take us through layers of superheated gas, past magnetic explosions larger than our entire planet, and down into a furnace where the very atoms of the universe are forged. Our mission is to understand what makes our sun tick. Why does it shine? Where does its incredible energy come from? Prepare yourself. We are leaving the familiar shores of Earth and plunging into the fiery, chaotic, and beautiful world that exists inside the sun. Our journey begins in the sun's outer atmosphere, the corona. From Earth, this layer is invisible, completely outshone by the sun's bright face. But during a total solar eclipse, when the moon perfectly blocks the sun's disk, the corona reveals itself. It appears as a stunning, wispy crown of light stretching millions of kilometers into space. It looks delicate, like a celestial ghost, but do not be fooled. This is a place of extreme temperatures. The surface below is about 5,500 degrees Celsius. The corona sizzles at 1 to 2 million degrees Celsius. That's hundreds of times hotter. How can the atmosphere be hotter than the surface? The corona is also the source of the solar wind. The gas is so hot and energetic that solar gravity can't hold it all. A stream of charged particles, mostly protons, electrons, escapes and flows outward through the entire solar system. The solar wind blows past Earth and drives auroras, northern lights, southern lights on Earth. Our first stop is a place of baffling contradictions. A near-perfect vacuum, far less dense than air, yet millions of degrees hot. Leaving the ethereal corona behind, we sink into the next layer of the sun's atmosphere, the chromosphere. The name means sphere of color during a solar eclipse. It appears as a reddish-pink ring. This color comes from hydrogen emission at a red wavelength. The chromosphere is much thinner than the corona, only about 2,000 kilometers thick. It is a chaotic, dynamic region, sits right on top of the sun's visible surface. The chromosphere is a forest of fiery jets called spicules, giant spikes of plasma thousands of kilometers high. They shoot up from below, then collapse back down in minutes. Hundreds of thousands cover the sun at any moment, making it look like a shaggy, burning carpet. Also where dramatic events begin, huge loops of plasma guided by magnetic field lines. These are called solar prominences. They can remain stable for days or even weeks. Sometimes those magnetic structures erupt, releasing vast amounts of energy and matter into space. Those eruptions are born from magnetic tangles rooted in and below the chromosphere. Think of the chromosphere as the turbulent ocean surface of the sun. Now we leave the sun's atmosphere and plunge into its interior. Next stop, the convective zone, the engine behind that boiling motion. We have now reached the photosphere. The name means sphere of light. It is the perfect description. This is the visible surface of the sun, the part we see when we look up at the sky with proper eye protection, of course. It is not a solid surface. The sun is a ball of gas. The photosphere is the layer where the gas becomes so dense that it is opaque. That means we cannot see through it to deeper layers. The light that warms Earth and illuminates our days is released from this layer. Up close, the photosphere is not smooth or uniform. It's covered in bright cells called granules. Each granule is about the size of Texas. Each granule is the top of a convection cell. Hot gas rises in the bright center of a granule. It spreads out across the surface. Then it cools, and finally sinks back down along the darker edges. This bubbling motion, granulation, makes the surface look like it's boiling. Each granule lasts only 10 to 20 minutes before being replaced. The photosphere is also home to sunspots. Sunspots are temporary dark patches that appear cooler than their surroundings. Sunspots mark regions of extremely strong magnetic field, thousands of times Earth's. Sunspots can be larger than Earth and can last days to weeks. They signal powerful magnetic activity churning beneath the surface. We now dive below the photosphere, into the upper region of the sun's interior. Welcome to the convective zone. This zone makes up the outer 30% of the sun's radius, a layer that's approximately 200,000 kilometers deep. The name convective tells you exactly how energy moves here, through convection. It's the same process you see when you boil a pot of water. The water at the bottom gets hot, becomes less dense, and rises. At the surface it cools, becomes denser, and sinks back down, only to be heated and rise again. This circular motion is called a convection current. Inside the sun, the same thing happens on a colossal scale. The material here is a thick, opaque soup of plasma. Photons of light struggle to travel through it. Hot plasma rises toward the surface in massive, slow-moving columns. The motion here generates the sun's magnetic field via a dynamo. Electrically charged plasma rises, falls, and is twisted by the sun's rotation, creating powerful electrical currents. Those currents produce the sun's massive, complex magnetic field. That magnetic field causes sunspots, solar flares, and other dramatic surface activity. Leaving the turbulent convective zone behind, we sink into a region of eerie calm, the radiative zone. This is the vast middle layer of the sun's interior, stretching from the edge of the core to the bottom of the convective zone. It is an immense region, making up about 45% of the sun's radius. Here, the plasma is incredibly dense, so compressed by the weight of the layers above that its density is greater than that of gold. The temperature ranges from 2 million degrees Celsius at its outer edge to about 7 million degrees Celsius as we approach the core. In this extreme environment, energy transport changes completely. In the radiative zone, the plasma is so hot and dense that the atoms are completely stripped of their electrons. This makes the plasma more transparent to radiation than the opaque soup in the convective zone. Energy no longer needs to be carried by the movement of gas. Instead, it travels in the form of photons, particles of light. However, their journey is anything but direct. A photon is emitted, travels a tiny distance, and is immediately absorbed by a nearby ion. That ion then emits a new photon in a random direction. This process is called a random walk. A photon does not travel in a straight line from the core to the surface. Scientists estimate that it can take a single photon on average anywhere from 100,000 years to 1,000,000 years to travel from the core through the radiative zone and finally to the surface where it can escape into space. We have arrived at our final destination, the core. This is the center of the sun, a place of unimaginable extremes. The core is relatively small, making up only the inner 25% of the sun's radius, but it contains nearly half of the sun's entire mass. The pressure here is over 250 billion times the atmospheric pressure on Earth. The density is more than 150 times the density of water. And the temperature is a staggering 15 million degrees Celsius, about 27 million degrees Fahrenheit. It is a furnace of cosmic proportions, the engine room of our solar system. In this crucible, the conditions are so intense that something truly remarkable happens: nuclear fusion. The immense pressure and temperature force hydrogen nuclei, which are just single protons, to overcome their natural repulsion and slam together. Through a series of steps known as the proton-proton chain, 4 hydrogen nuclei are fused together to create one helium nucleus. This process is not perfectly efficient. The resulting helium nucleus has slightly less mass than the 4 original hydrogen nuclei. This tiny amount of missing mass is not lost. It is converted directly into a tremendous amount of energy. According to Einstein's famous equation, E equals mc squared. This is the secret to the sun's power. Every second, the sun's core fuses about 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons of mass are converted into pure energy. This energy, released in the form of high-energy photons, gamma rays, and tiny particles called neutrinos, is what powers the sun, and, by extension, all life on Earth. This process has been going on for 4.6 billion years, and the sun has enough hydrogen fuel in its core to continue shining for another 5 billion years. The energy created here in the core is the starting point for the journey we have been tracing backward. The energy generated by fusion does not just produce a steady stream of light. The turbulent motion in the convective zone, powered by that energy, creates powerful magnetic fields. Sometimes, these magnetic fields become so twisted and tangled that they snap like a rubber band, releasing a massive burst of energy. This is a solar flare, one of the most violent explosions in our solar system. A single flare can release the energy equivalent of billions of nuclear bombs, sending a flash of X-rays and high-energy particles hurtling into space. Sometimes these eruptions are even bigger. They can blast billions of tons of the sun's own plasma out from the corona and into the solar system. This is called a coronal mass ejection, or CME. A CME is a giant cloud of magnetized plasma that travels through space at millions of kilometers per hour. If a CME is aimed at Earth, it can have significant consequences. It takes about 1 to 3 days for this cloud to travel from the sun to our planet. When it arrives, it slams into Earth's magnetic field, the magnetosphere which normally protects us from the solar wind. The impact of a CME can trigger a geomagnetic storm. These storms compress our planet's magnetic shield and can induce powerful electrical currents in the ground and in our atmosphere. The most beautiful effect of a geomagnetic storm is the aurora, the northern and southern lights. As charged particles are funneled down Earth's magnetic field lines near the poles, they collide with atoms in our atmosphere, causing them to glow green light, pink light, red light. However, these storms can also be disruptive. The electrical currents they induce can overload power grids, causing widespread blackouts. They can damage satellites in orbit, disrupting GPS communications, weather forecasting. They can even pose a radiation risk to astronauts on the International Space Station. Our journey to the center of the sun and back is now complete. We have traveled through ghostly halos, fiery forests, boiling seas of plasma. We have navigated a million-year-long maze of light and witnessed the cosmic furnace where atoms are forged. We have seen how the sun is not just a distant ball of light, but a dynamic, complex star whose every tremor can be felt across the solar system, right here on Earth. The sun's story is not just a tale of astrophysics, it is our story. The fusion in its core is the ultimate source of the energy that makes our world habitable. Every time you feel the warmth of the sun on your skin, you're feeling the end result of a process that began deep inside the core millions of years ago. The light that allows plants to grow through photosynthesis, forming the base of our entire food chain, is ancient light from the sun's heart. Weather patterns on Earth, ocean currents, the wind. We are, in every sense, children of the sun. Our planet exists in a delicate balance, orbiting within the sun's life-giving habitable zone. The sun is currently fusing hydrogen into helium. Other larger stars fused helium into carbon, into oxygen, and into the heavier elements necessary for life. When those stars died, they scattered these elements across the galaxy. Our sun and its planets were formed from the recycled dust of these ancient stars. The carbon in your body, the oxygen you breathe, the iron in your blood, all of it was forged in the core of a star that lived and died long ago. We are not just living off the energy of a star, we are made of stardust. So the next time you look up at the sun, I hope you see more than just a bright light. I hope you see the layers of its atmosphere, the boiling surface, the deep zones of energy transport, and the incredible fusion reactor at its core. I hope you see the source of the energy that animates our world and the cosmic factory that connects us to the universe. Our journey to the center of the sun is a reminder that we are part of something vast, powerful, and profoundly beautiful. We are connected to the cosmos, and the proof shines down on us every single day. The next time you step outside and feel that familiar warmth, remember the incredible journey that light has taken. From the nuclear furnace at the center, through the million-year maze of the radiative zone, up through the churning convective zone, across the boiling photosphere, through the fiery chromosphere, and out through the ghostly corona. That ancient light, born in the heart of a star, has traveled across space and time to reach you. You are not separate from the cosmos, you are part of it. And every day the sun reminds us of that profound and beautiful truth.